Alright guys, I'm sorry we're picking back up in a new video because the pause button did not pause. It stopped the recording. I thought I had a pause, but I did not. So we got our line graphed with this positive slope. Let's switch and do number 4. Y equals 3, so we're interested in a line where I've got all of the y values of 3. Well, my y equals 3 is right here. Y equals 3 is also all the way across here. Hopefully you remember the type of function this is. This is my constant function because y is equal to a constant. It's a horizontal line. My slope is 0. My y-intercept here is 0, 3. My domain and range, we didn't list domain and range over here. Domain and range for this graph, all real numbers, just like it was for the other two. My domain and range here are not both all real numbers. My domain is still all real numbers, but my range is limited to that single y value. That's the only y value for which my function exists. So my range is just 3, positive 3. All right, that is all of our graphing of linear functions. Now we're going to do the next 4. We're going to practice transformations of functions that are not linear. We're using those parent functions and our pattern of transformations to figure out what we're doing. Now, remember your pattern of transformations. And I'm going to write it on a post-it because I didn't leave enough space here to write it where we're working. My pattern of transformations, y equals, and then whatever's going on with the function, with that, whether that's a square function, cubed function, if these are absolute value bars, square root, I have x minus, and then I've got some horizontal shift. So that's going to be my left, right horizontal shift. Notice it starts x minus, so it goes the opposite way we expect. If I plug in a 2, a positive 2, that's going to be x minus 2. That shifts us to the right. If I plugged in a negative 2, x minus a negative 2 becomes x plus 2. That shifts us back to the left. So just keep that horizontal difference in mind. Then we've got plus k tacked on at the end, just not attached to the x, just added on at the end, or it could be at the beginning. But that's going to be my vertical shift. Up, down. And it goes, because it starts out as plus, it goes the direction we expect it to go. If I have a coefficient out front, that's my vertical stretch or shrink. It's a vertical stretch or shrink. And it's a stretch if it's a whole number, and it's a shrink if it's a fraction. It's a stretch if it's a whole number, it's a shrink if it's a fraction. Finally, we've got reflections. Reflections can show up here. If I have a negative out front, it reflects on the x-axis. If I have a negative inside whatever's going on with my function, it reflects on the y-axis. And when you have a reflection, you have to tell me which axis it reflects over. Okay, so let's move that over, and we're going to start with this one. Well, my parent function here, okay, and this is very important. Again, make sure you're reading instructions, using transformations to graph with its parent function, and then we're going to go and we're going to give the domain, range, and intercepts. Now, I have lines for those so you don't forget on this assignment, but I don't always have that. When you graph the parent function, I'm going to graph all my parent functions in green. This is my square root function. It's a square root function, and the parent function is right here, that half parabola y equals square root x. That's my parent function. Now my transformed function has a negative out in front. That negative out in front tells me that I'm going to reflect this parent function on the x-axis. So it's going to keep the same shape as much as I possibly can show that it keeps the exact same shape. It just reflects across. I've reflected it the wrong direction. Guys, it's going to be possibly a long day, and I don't have any whiteout. Oh my goodness. Okay, so hold that thought. I'm glad I noticed it before I went on. This is wrong. This is wrong. This is the y-axis, not the x-axis. reflects on the x-axis. So as you guys make mistakes, just give yourself grace. Please give me the same grace. This is my reflection on the x-axis. This is the right way to reflect. I hope that you are all sitting at home going, wait a minute, she's not doing that right, because she wasn't. Okay, here it reflects on the x-axis. This is my transformed function. Y equals a negative square root x. All right, domain. The domain of the parent and the transformation in this case are the same, but we're giving the domain of the transformed function. The domain is from 0 to positive infinity, because that's the set of x values that I'm using. The range is different. For the parent function, the range would be 0 to positive infinity. For the transformed function, the range is from negative infinity to 0. Now, remember that this order definitely matters. You always go least to greatest. You start with the lowest end, you end with the upper end, the upper limit in this case, the high end. If you did 0 to negative infinity, if you wrote it down backwards, that's wrong. So make sure that you write your everything from least to greatest. The y and the x-intercept, where it intercepts the y and the x-axis, is that same point for this function. It's at the origin, 0, 0. All right, let's cover up that mistake and move on. So now our family of function here is our absolute value function. And absolute value is a v, and I'm going to start by graphing my parent absolute value function. I've got this v, y equals absolute value x is my parent. Now I'm going to look to see what transformations I'm doing. Inside is my horizontal shift, and it goes the opposite direction that I think it's going to go. So I would think about taking this x plus 1, setting it to 0. X is a negative 1. I'm shifting it to the left 1 unit. And then this is my vertical shift. It's going to go up 2 units. That vertical shift goes the way we expect it to go. So this vertex at the origin is going to shift to the left 1 and up 2. My new vertex is at negative 1, 2. That's the new vertex. Now my absolute value function needs to stay about the same opening. I don't want it to visually look any wider or narrower than the original. My domain and range I'm giving for the transformed function. Domain and range of absolute value, domain, not range. Domain of the absolute value is all real numbers. If it starts all real numbers, it stays all real numbers. But my range has a limit. For the parent function, that limit is 0, but I just shifted it up 2, so that limit has shifted with it. My range for the transformed function is 2 to positive infinity, and 2 is included, so it's in square brackets. Now, let's talk about intercepts. My transformed function is up above the x-axis, so there is no x-intercept. It does, however, have a y-intercept. My y-intercept always happens where x is 0, so I'm going to do just a little bit of math here. I'm going to say where x is 0, in this function I have y equals absolute value of 0 plus 1 and then plus 2. Well, the absolute value of 1 is 1, 1 and 2 is 3, so my y-intercept is at 0, 3. Okay, now let's move down to the next one. My parent function here is the squared function, quadratic function, y equals x squared. So I'm going to graph my parent function, y equals x squared. That is required by the assignment, so make sure that you're paying attention to the instructions. Then I figure out my pattern of transformations. Well, my transformations here, I have a coefficient out in front, and it's a whole number. So I have a vertical stretch by a factor of 2, vertical stretch. And then I've got this tacked on at the end, a minus 1, so it's going to go down 1 unit. So I'm going to take my vertex here at 0, 0. I'm going to shift it down 1 unit to negative 1. And then my stretch, if I think about grabbing and pulling this out, it's going to get skinnier. So my vertical stretch makes it look visibly more narrow, this new parabola, as compared with the parent. All right, domain and range. Domain of a quadratic function is all real numbers. Oh my goodness gracious, guys. I have an erasable pen. I totally could have fixed my mistake over here with my erasable pen. I need you guys in class with me to keep me honest. There we go. All right, I fixed my mistake. It looks much better up there. I've got my erasable pen. I've got my domain for all real numbers for this function. Now my range has a lower limit. The range limit for the parent function starts at 0 and goes to positive infinity. I'm still going to positive infinity, but since I shifted it down, that limit shifted as well down to -1. Now I do have a y-intercept. My vertex is sitting on the y-axis, so I have 0, -1 for my y-intercept. To figure out my x-intercept, I need to plug in 0 for y. So I take my function and I replace y with 0. Excuse me. 2x squared minus 1 is equal to 0. I'm going to solve that. I'll add that 1 to move it over. So I have 1 equals 2x squared. I need to divide both sides by 2. So now I'm out of space there. So let me move down. I've got 1/2 equals x squared. And I need to use the square root property to solve this. So I take the square root of both sides. When I take the square root to solve, I have to consider plus minus. That gives me both my positive and negative y-intercepts, or excuse me, x-intercepts. I have one here and I have one there. They were equally spaced around the y-axis because it's balanced on it. It's could be folded on the y-axis. It has that even symmetry. So plus or minus square root of -2. I can simplify the square root of 1 would be 1. We're just going to leave it like that. We're going to say, you know what, I've got a positive square root of 1/2 and I've got a negative square root of 1/2 as my x-intercepts. We're not gonna mess with this radical right now. Square root of 1 would be 1, so I could write it as 1 over square root 2. That invites me to do what we call rationalize the denominator, and we haven't talked about that yet. So we're just going to kind of let that hang out there like that for today. Those are the values of my x-intercepts. All right, last transformation of a polynomial function here. I've got a another square root. I've got another square root function here. Maybe I don't have a reflection, so I don't have to worry about messing that up this time. Y equals square root x is my parent function. And then when I look at my transformations, this transformation is a vertical shrink because it's a fraction. It's going to be a compression or a shrink by a factor of 1/3. Now, when I do a compression, a vertical compression, I think about taking this and squishing it. So when I take this shape and I squish it, it's going to flatten out. And then the other transformation I've got is attached to that x value. So this is a horizontal shift. And it's x minus 1. It starts as x minus, so I've plugged in a positive 1. So it's going to go to the right 1 unit. So I'm going to take this vertex, shift it over 1 unit to the right, and when I sketch it, I'm going to flatten it out. So it's not going to go up as fast. It's going to be much flatter. My domain has shifted from 0 to 1, still going to positive infinity. My range hasn't changed because I didn't have a vertical change, a vertical shift. My range still starts at 0 and goes up to positive infinity. It's just going up more slowly. Y-intercept, well, I moved it over to the right and it goes to the right, so I do not have a y-intercept. There is none. My x-intercept is right there, 1, 0. All right, excellent. Good job, good job. Let's look at that next page, and we're going to start talking about what we call piecewise defined functions. Now, a piecewise defined function takes my domain and it breaks it into different pieces. So I have different equations or rules assigned to different pieces of the domain. Different equations or rules apply to different pieces of the domain. Now it is possible that when we split our function at a certain value in the domain, we could choose to leave that out, and then our domain would be missing a value. But you can see here that this 1 is included in the first piece. This is less than or equal to. So since the 1 is included in this piece, it's not left out of the domain. And my domain is all real numbers. Now we're going to graph this piecewise function. We're going to use a different color to graph each of the 2 different pieces. And when we start and stop our graph, we are going to go all the way to 1 in this case. We're going to go all the way to where that domain breaks and changes, even if it's not included in that piece, because otherwise this is our limit. It goes up to but does not include 1. We've got to have an open circle there to show that it goes up to that point, or it starts just past that point. Alright, my first piece of the domain, this first line, is x values less than or equal to 1. And my rule for this piece of the function, f of x is equal to x plus 3. So y is equal to x plus 3. Well, what shape is that? X plus 3 is a linear function, and it has a slope of a positive 1. So I know that this piece of the function for x values less than or equal to 1 is going to be a line with a positive slope. Well, where is this going to happen? It's going to happen from negative infinity up to x is 1. So it's going to happen on this left end of the graph all the way to where x is 1. Let's see exactly where that's going to fall. Now I know I've got to go all the way to 1, so that's my biggest x value that I'm going to use is 1. Let's pick a couple of others that fit in this piece of the domain. Well, values less than 1. 0 is always good to use. 0 is less than 1. I can pick any negative number over here. Let's just do negative 4. There's no magic value there. We just grab something out of this piece of the domain. Well, if x is negative 4 and 3 is negative 1. If x is 0, 0 plus 3 is 3. And then this is my stopping place. This is my upper limit. If x is 1, y is 4, because 1 plus 3 is 4. So let's get this piece of the function graphed. It's going to be a line with a positive slope, and it's going to stop at this point. And I get to include that point because it's or equal to here. So I've got negative 4, negative 1. I've got 0, 3, and then I've got this stopping point at 1, 4. I'm going to fill it in because it is included in that piece of the graph. And when I draw my line stops here where x is 1. So that is just going to have one arrow on the end, not an arrow on the other end. This is why arrows are important to us. Okay, let's change colors for the other piece of the function. For all of my x values greater than 1, my y value, or my function value, is 4. 4 is a constant. So no matter what x is, y is going to be 4. Hopefully by now we know the shape of that constant function. Well, my first x value is 1, but 1 is not included. So I'm going to do these squiggles to show myself that I need an open circle there. That's my reminder that when I use this point, it's going to be open, not filled in like it was here. And then it's a constant function. Let's just pick another piece of the domain. X is 1. I can pick any value over here I want, any x value, all the way to whatever, 1,000, 1,000,000, but those don't fit on my graph. So let's maybe 3. X is 3. That's right there. No matter what x is, though, I've got the constant y is 4. So when I go to graph this piece, it's going to start at this point 1, 4, and that's going to be an open circle. So at 1, 4, I have an open circle for this piece, and then it's going to go all the way to where x is positive infinity. So I have an arrow on that end. That's what this piecewise function looks like. Now, we already did domain. Domain is all real numbers. What about range? Well, as I read my range from negative infinity on the y-axis going up, this is always going to exist all the way down to negative infinity. So my range is going to be from negative infinity up to and including, because this value is included in one piece of the graph, up to and including the y value 4. That's the range for this function. Now, if you're a little lost, if you need to slow down, do it. Slow down, rewind the video, go back and rewatch that. But we're going to go ahead and move on and do this next piecewise defined function. Once again, we have split our graph into 2 pieces. This time the split happens at negative 2. but negative 2 is included in this first piece, which means that my domain does not leave that out. My domain is still all real numbers. My first piece of the function is right here. All x values less than or equal to negative 2, and the rule for that piece is again x plus 3. So f of x is x plus 3. So we just did that one up here. We know what it's going to look like, but we can't go all the way to positive 1 with it. We have to stop at negative 2. So if we stop at negative 2, that means I could still use this point, negative 4, negative 1, because that's in the right piece of the domain. I've got to go all the way to negative 2. We're just going to use negative 2. We know it's going to be a linear, it's going to be a straight line. We only need 2 points to define a line. So this is included in this piece, or equal to. If x is negative 2 plus 3 is a positive 1, that's where my line is going to stop this time. So let's do that. Let's fill that in. At negative 2, I'm at positive 1. It's filled in because my line stops there. And I know it goes through the point negative 4, negative 1. That's enough to draw my line. My line is going to stop at that point where the domain ends. It keeps going all the way down to negative infinity. And we're ready for the other piece. Now, this other piece, this second piece of this function, is quadratic. It's for x values greater than negative 2. And I've got my parent function shrunk by a factor of 1/4. So f of x equals 1/4 x squared. Okay, greater than negative 2. So it's going to be this right-hand piece of the graph. X negative 2, I got to use that, but it's going to be open circle. It's not going to be filled in. Now, there are no magic x values to plug in, but I know that whatever I do here, I'm going to square it, then I'm going to divide by 4 because I'm multiplying by 1/4. So let's do a positive 2 because I know that that's going to fit. 0 is good. What's the shape of this graph? Well, it's a parabola because it's x squared. And I haven't shifted the vertex. I've just stretched it. So like the parent function, it's going to sit right here. If I do 0 squared is 0, 0 times 1/4 is 0, there's my vertex. What about negative 2? Negative 2 squared is 4, and 4 times 1/4, negative 2 squared times 1/4. Negative 2 squared is 4, and 4 times 1/4 is just 1. So at negative 2, I'm up here at 1. Oh, look at that. That's that point already. This time it needs to be open circle. And then if I go to positive 2 squared is also 4. And 1/4 of 4 is still 1. So at 2, I'm up here at 1. And then I see that I have this kind of really wide open, smushed, compressed parabola. But I only draw the part of the parabola that fits in this piece of the function. So I don't have the whole parabola. Okay, our domain was all real numbers. If I look at our range, I see that this end keeps going, this end keeps going. So for this piecewise function, my range is also all real numbers. All right, let's switch to the last page here. We've got a final piecewise function that we're going to graph, and then we've got an application problem. 2 pieces again. This one splits the domain at 1. I want to encourage you to pause the video, give it a shot on your own, see what you come up with, and then come back and see what we did. 1 is included, so we haven't left it out. We could, but we didn't. Our domain is going to be all real numbers again, all real numbers. My first piece of the function is from x less than or equal to 1, and the rule f of x is a negative absolute value of x. So, absolute value function, I've taken my parent function and I've reflected it across the x-axis. Well, my parent absolute value function is a v that goes up. If I flip it over, it's going to go down. So I know the shape of this piece. It needs to stop at positive 1. So it's just going to be this piece. It's not going to be the right-hand side. So if we've got x values less than or equal to 1, let's do maybe a -3 and a 0, and I got to stop at 1, and I get to include it. Now the absolute value of -3 is 3, but then I've got that negative out front, so that makes it a -3. That's that reflection. Absolute value of 0 is 0. 0 isn't positive or negative. That's my vertex. And then I've got the absolute value of 1, but then the negative out front makes that a -1. So this piece of the domain at -3, I'm down here at -3, 0, 0, that's my vertex. And then I've got this 1, -1, it's included, so I use the filled in point, and that keeps going forever down. That is this first piece of my function for the domain from -infinity up to 1. Now at 1 it shifts and we have a new piece, a new rule. For x values greater than 1, I'm using the rule 2x. Well, what is that shape going to be? It's just x, so that's linear. And it's got a positive slope, so it's going to be an increasing function. Starting at 1, but not included, open circle there. And then I need another x value that's in this piece of the domain. I can pick anything. Let's pick 5. 5 sounds good. Oh, 5 may be really big. 2 times 5 is 10. Does 10 fit here? 1, 2, 3, 4, 5. That's off our graph. Let's pick a smaller value so I can be exact on my graph. Let's pick 3. 6 is there. 2 times 3 is 6, so that's a point on my graph. 2 times 1 is 2. That's my open circle where I start. So 1, 2 is my open circle for this piece of the function. 3 and 6, so 1, 2, 3, and then up 2, 4, 6. That point is on the graph. So this piece of the function looks like this. Now notice that they don't meet. That's fine. My range has a gap in it, so we're going to have to pay attention as we list our range. But it's okay that they don't meet. This piece ends in a filled-in circle because that value for x is included. This piece starts with an open circle because that value for x here is not included. Included, not included. Okay. Let's do this for range. My range, as I start down here at -infinity, my function exists because it's going on. I got that arrow. It goes up to 0, and then there's a gap. So when I'm writing my range, I say, okay, -infinity up to 0, 0 is included, but then there's this gap. So I say, or, that's my union symbol. My range picks back up at 2 with an open circle, so not included 2, and then it keeps going all the way up to positive infinity. There's my range for that piecewise defined function. Okay, excellent, excellent. Let's do this application problem, and then we are done with 3.2. And we really haven't done a lot of, I guess piecewise functions are new, but we're really just putting together things that we already know how to do with transformations of functions. Okay, so take a second and read the setup for this application problem. I don't know that cell phone plans do this anymore. Most people do more texting than talking, so I'm not sure. But at least a long time ago, cell phone plans used to charge sometimes by the minute if you didn't want an unlimited plan. So we've got 2 different plans, and we need to decide which one is better. And that may not be just one plan. It may be that one plan is better up to a certain number of minutes, and then one plan is better after that. Now these plans, each of them separately, give us piecewise defined functions. So we're going to do plan A in red. And we're going to say, okay, $30 a month buys 120 minutes. So we're going to call this function f of x. I guess we could call it a of x because it's plan A. Let's do that. That'll be fun. A of x is, and then it's piecewise defined. So we've got 2 rules going on. It's just $30 a month as long as I have less than or equal to 120 minutes. So we're going to have minutes as our X values, dollars as our Y value. So let's go ahead and let's think about minutes be our domain, cost is going to be our range. Now what if we go over 120 minutes? Well, the first 120 minutes are included here. So we have to consider that when we set up our piecewise defined function. So let's think about that for a minute. Let me grab a piece of paper. If I have $30 and then if I go over my 120 minutes, I'm going to be charged 30 cents for the time I go over 120. So plus 30 cents for X values that are greater than 120. So I have to subtract out that 120 because I've already paid for that first 120 minutes here. So I'm only going to pay 30 cents a minute after that 120 minutes. So like if I talk for 200 minutes, 200 minus 120 is 80. I'm only going to be charged extra for that extra 80 minutes. Let's clean this up a little bit now that we see what it looks like. We need to distribute this. So I've got 30 plus, and then 0.30x minus 3 times 12 is 36. Where does my decimal need to go? Well, my decimal is going to go if I just do the 0.3, my decimal goes here. Oh, so it's going to be 36. So minus 36. I'm trying to decide if I like that or not. I didn't divide that out like that when I had 0.3 times negative 120 is a negative 36. Yep. Okay. So we've got 0.30x minus $6. So let me check something here. If I have 200 minutes, that'd be times 0.3, and then, yep, that works. Okay, checking my math, making sure I've got it set up the right way. So this is going to be how much I pay after that 120th minute. Now that looks cheap, but I'll tell you what I did. I plugged in 200 minutes and I said, okay, if X is 200, so I'm finding A of 200 minutes. Well, that is 30 cents times 200 minus $6. And 0.3, get where yours not a glare, 0.3 times 200 minutes, and then minus $6. So at 200 minutes, my plan is going to cost me $54. Now remember, this piece only applies after that 120 minutes. So that's when we're going to start applying this rule for the cost of my function, the cost of my cell phone plan. All right, let's go ahead and graph this one, and then we will fix the other one up and graph it. So let's we're going to need to set up our domain and range. We're going to need to decide what we're going to count by. I know I'm going to need to go up to 200, 300 minutes, so we're going to count by 20s. So if this is 0, my first line is 20, 40, 60, 80 minutes, 100, 120, 140, 160, 180, 200 minutes, 220, 240, 260, 280, 300 minutes. I think that I tried like 360. So we're going to go ahead. This goes all the way to 400 minutes if I count by 20. So that works out nicely. Now with money, I know that my plan is going to cost $30, $40. I just came up with a cost of $54. I think we can count by fives here on my vertical axis. I can count by fives, so that's $5, $10. That'd be $15, $20, $25, $30, $35, $40, $45, $50, $55, $60, $65, $70, $75, $80, $85, $90, and then that would be $100 for the cost of the plan. Okay, so let's go ahead and graph this piecewise defined function for plan A. We know that it's going to cost $30 up to 120 minutes. Now, I only have positive values because we can't talk negative minutes and we can't pay negative dollars. So my plan A is going to cost $30 until I get to 120 minutes. So from 0 to 120 minutes, plan A costs $30 right there. Now what about if I go over 120 minutes talking? Well, let's see. Plan A then costs 30 cents a minute minus $6. Now we just did the calculations for 200 minutes. At 200 minutes, we said it cost $54. Let's go to 300 minutes and see what happens at 300 minutes. Well, right here, 300 minutes, so 0.3 times 300 minutes, and then I subtract that extra $6, and I'm at $84. So if I talk 300 minutes, we're at $84. Now, this is linear because it's just x, so I only need those 2 points to get me there. I know that I'm going to start at 120 is $30. That's my jumping off point there. If I go to 200 minutes, I'm at $54. So that's 50, that'd be 55, make that 54. If I go to 300 minutes, I'm at $84. So I go up to 80, 85 would be there, so that would be 84. So this is going to be the line that gives me the cost of plan A. So it gets more expensive the more I talk, which is just to be expected, right? Okay, so now let's look at plan B. So plan B, we're going to do B of x for our piecewise defined function. Plan B starts out at $40 a month, which is more, but that buys us 200 minutes. So it costs $40 a month if I talk up to 200 minutes. And then after 200 minutes, it's just $20 a minute. So let's figure out what that's going to look like. It would cost $40, and then it's going to cost an additional 20 cents a minute after that 200 minutes. So I need to figure out what's going to happen after 200 minutes. So I'm going to distribute that, and I have 40 plus 0.2x minus, well, 2 times 2 is 4, but when we get decimals into it, let's just be safe. We've got 0.2 times 200 minutes. That would be that's a minus, but it's a negative 40, right? So minus 40. So the 40 and 40, so it's just 2 cents a minute extra after that 200 minutes. It's going to be 2 cents a minute extra after that. 20 cents a minute, not 2 cents. Oh my goodness. 20 cents a minute after 200 minutes. Good grief. Wrong inequality symbol. First piece is $40 less than or equal to 200 minutes. Second piece is 20 cents a minute after 200 minutes. 20 cents a minute after 200 minutes. After 200 minutes. So, like, we're going to have 300 minutes. That if we talk for 300 minutes, then that is going to be 0.2 times 300. Our plan is going to cost us $60. So that $40 is factored in, and then we're going to pay $20 more for that extra 100 minutes that we're talking. Okay, so we said if I talk 300 minutes, it's going to be $60. Let's set up our piecewise there. So if I'm going over 200 minutes for this plan B, B of x charges 20 cents a minute, so after 200. So if I talk 300 minutes, that plan is going to cost me $60. Let's graph our first piece here, up to 200 minutes. So up to 200 minutes, this plan B costs $40. So $40, 200 minutes, up to 200 minutes, plan B is more expensive. Ooh, look right there, we cross. If I talk for 300 minutes, it's going to cost me $60. So let's go up to $60. What about if I talk 400 minutes? Well, 400 times 0.2 gets me $80. So 400 minutes gets me at $80. Ah, now look at that. So when I compare the two plans, Plan A starts out as a better deal. It starts out cheaper. But when we get to this point right here, they switch. Plan A is cheaper until we get to 160 minutes. At 160 minutes, after that point, Plan A is more expensive and Plan B is cheaper. So the $40 a month is more expensive unless you're going to talk more than 160 minutes a month. If you're going to talk more than that, that ends up being the cheaper plan. If you're going to talk less than 160 minutes a month, Plan A is a cheaper plan. So sometimes the best deal is not straightforward. You can't just say, oh, it's always this one. Sometimes it depends. All right, that is it for section 3.2. And remember, you can go back and rewind and rewatch if you need to. And I will talk to you later.